Greetings everyone. In this example we're going to talk about building a scatter plot, conducting simple linear regression, and identifying the correlation coefficient, coefficient of determination, and the standard error of the estimate using Excel. So, regression is a powerful tool that ideally helps us make predictions, and I'm going to walk through a problem where regression is ultimately used to analyze the proposed expansion of a supermarket chain. The supermarket chain is considering expanding into a new community. So imagine that you are the director of planning and must present an analysis of the proposed expansion to the company's board of directors. One element of your analysis includes information on the relationship between the amount spent for groceries in a household and income. So let me say that again for those in the back. You're currently investigating the relationship between grocery expenses and income. So you're going to want to open that supermarket data set in Excel. So first things first, let's just see if there's a relationship by creating a scatter plot in Excel. And to do this, we're going to highlight our variables, which are amount and income in columns B and C here. And then I'm going to go to the Insert tab. And then I want a scatter plot, and this is the scatter plot icon. I'm going to click the drop down here. And as I mouse over, I can see different versions of this type of chart, but I want the oldie but goodie, our original basic scatter plot. So pause for a second and ask yourself, what kind of relationship is this? How strong does the relationship look? Well, this appears to be a pretty robust positive relationship based on the direction and shape of the data. We don't know the exact details, but it seems like this is a relationship we should continue to investigate. So let's run a simple linear regression on the data. This is a simple linear regression problem because there is only one dependent variable, which is amount, and only one independent variable, which is income. So to do this, we're going to navigate to the Data tab. We're going to click Data Analysis. We're going to go down to Regression. You may have to scroll up or down to get to it. Click OK. And now we have a dialog box to populate with our data. So Excel here has already filled in some of the blanks for me. The Y range, this is the dependent variable, so that's what's in column B in cells B1 through B41. And I can just highlight them like that. Now it looks correct. We do the same thing to highlight the X range, which in this case is C1 through C41. The very first row includes the name of the variable, so you need to make sure you click Labels here. Otherwise, it's going to throw you an error because you can't regress words. And then, if I want to see the output on the same sheet as my data, I will click Output Range. And it has E19 populated, but E19 appears to be covered up by my scatter plot, so I'm going to click that field and choose E24. Oh, E24, there we go. I'll click OK, and now I have the output of my linear regression model. So there are some results here that help us better understand the relationship of these two variables. The coefficient of determination, which is labeled as multiple R, and correlation coefficients range from -1 to +1 with simple linear regression, but only 0 to 1 with multiple linear regression. So as the value gets closer to 1 or -1, the relationship is closer. These variables move together in a consistent pattern. One way to verify the significance of that value in a simple linear regression model is to look at the t-statistic of the independent variable. So our independent variable is income, and it's shown down here with its results. And this is its t-statistic. That's 17.76586. And we can evaluate its significance by looking at its p-value, which here is a very small number. Whenever you see a number followed by the letter E and a minus symbol, that's how many zeros go in front of the first number in that value. So in this case, this is 0.19 zeros, 532. So that's a very small number. It is a lot smaller than 0.05, which is usually the p-value you're looking for. That's usually the level of significance that you're interested in. So because this number is so much smaller than 0.05, we can be pretty confident that this is a very significant relationship. Two other measures that we can use to evaluate the relationship in the regression output are the coefficient of determination, which is listed as r squared. It's not quite as high as the correlation coefficient, but they're both very high numbers and both do suggest a tight relationship. We have a standard error of 82.32849. This is the standard error of the estimate. And this comes in handy when you're comparing models that are predicting the same dependent variable but with a different or a set of different independent variables. That adjusted r squared value we don't use in simple linear regression. It's usually the same or very close to r squared, but it takes into account the number of independent variables. So if you're comparing models with different numbers of variables, that adjusted r squared value becomes very, very important. So what does this information tell us about the relationship between these two variables? Well, it tells us that there is a significant relationship, that these variables move together in a consistent manner, and this means that this could really be an important element in our analysis of expanding into a new city.